So my name is Greg Zarus. I'm with the Agency for Toxic Substances and Disease Registry. So we're a small agency that's part of the Centers for Disease Control. I'm working with colleagues from the National Center for Environmental Health in our Microplastics work group, and we're just exploring this. We're far from experts too. We've been looking at other kinds of toxic substances, and we're going to see what we know about the way we look at other toxic substances that we can apply to microplastics. Let's see where. Okay. So the topic is data needs to evaluate human exposures to microplastics in air and water. And also, second spoiler, it's insufficient. So the data is insufficient for us to evaluate it at this time. Maybe if I stand a little away. Disclaimer, nothing that I say today is really represents the policy of my agency because we have no policy on microplastics right now. So brief outline. Is that a dot? Oh, sorry. Oh, there it is. Well, disclaimer, then we'll go back to, so outline is, I'm going to look at both of our centers that make up the Microplastics Workshop, National Center for Environmental Health, and ourselves. I want to differentiate the way we look at toxic exposures. Then I want to differentiate what ATSDR and EPA each do at a site, because we both look at site-specific or case-specific exposures, and we look at it a little differently. And I think in explaining that, you'll understand why I'm using a very narrow lens at how we look at toxic exposures, and I want to try to apply that to microplastics, because it seemed too big a problem when we heard it this morning. So I'm going to look at it a little focused avenue of information. So of course there's a lot of information about our missions. Our united mission is to safeguard human health from environmental threats. And I'm just going to look at the first row here. NCH prevents illness, disability, and death from contacts between people and their environment. And ATSDR protects communities, so that's a big key, communities from harmful health effects associated with exposure to hazardous substances, both natural and man-made. So the main issue is NCH looks at the U.S. as a whole, looks at all of our exposures, and uses information from many individuals. ATSDR looks at case-specific examples or community-specific examples. So often, again, there's differences between us and EPA. They are a regulatory agency. We are a health advisory agency. So I want to look at the row number 2, which says, because this is where people usually confuse us, because we both use risk assessment tools. We use them to use risk calculations to determine possible health effects of exposures from the past, the present, and future, regardless of the source of chemicals. But we focus first on the source. And then EPA performs risk assessment too, but very site-focused, and it's really the purpose is for risk management, so they assess it to determine cleanup levels. That's when we both work on a site together. So there's a process. So actually we have a couple different products. One product would be, you might know us for the Toxicological Profiles, which is all the published studies and what they mean for us regarding human health on a certain substance. Here, this doesn't say microplastics, it says creosote. I could hold one up for PAHs, so it's also groups of chemicals that we can make analogies from when we look at microplastics. So we are brought to the dance. We're brought to a site from some way. We have to do Superfund sites, but EPA brings us to certain sites to evaluate health effects. And then sometimes the public has enough information in themselves for us to investigate a small community. They provide us data, and it could be air, water, soil, or local fish. Not the ones from the grocery store, but fish that might be contaminated as a result of a spill. Then we conduct an assessment. And so it's these 2 items I'm going to focus on today. We provide recommendations, and usually it's to reduce exposures. Sometimes, quite often, it's nobody's exposed. And then the other one would be to reduce the uncertainty because we can't make a conclusion based on the data that's provided. This is our pathway assessment tool. We are so lucky to look at things this way, and that is start at the contaminant source and follow it all the way into the people and see if it makes an effect. NCH is often starting from the other end. How much is inside people and where does it come from? That's a really hard hard problem to solve. So with these pictures, I hope to demonstrate a little bit of something of exposure. Here we could either launder my polyester clothing and I will breathe the particles, which I've already sampled to see that sure enough there's a lot of microparticles that come out of my dryer. Or I could wash them and it goes through our sewers, wastewater treatment plant. They compost it and some of those solids are applied to lands that wash into our creeks and maybe wind up in the oysters I eat. We'll hear more about bivalves later and their concentration, but clearly we can see, hey, it makes sense, I might be exposed. So how can I apply our exposure policy method to demonstrate what kind of data is lacking in the microplastic data in our environment? And we've heard these. Brockman's lab has wonderful data for ecological studies. In fact, it's one of the few that provide me a mass of particles. I have both mass and I have particle number, but unfortunately it's in the fish gut, as we've already heard, and so I can't really translate it to Greg's exposure. 115 cups in the whale is pretty bad for the whale, but again, I can't evaluate exposure. Although it does make me interested about some tribal communities, what kind of effect, since they're already affected with massive accumulation of all the other persistent organic pollutants, what they'd be exposed to since these microplastics are accumulating up in these food chains. But other studies, a great air study helps me understand transport. 249 microparticles are deposited per square meter a day. But again, what's that mean to what I inhale? We have very few studies, and I could have mentioned Bart's work earlier, but we choose Kosuth's work on microplastics from 159 cities, and we find somewhere around 9 microplastics per liter. So I know, my glass was just taken, that from that glass of water, I probably got 4 microplastics from it. So there was some degree of exposure, but what does that mean? And then we all brought up the tea. I think everybody's brought that. It's an easy picture that we can say. I certainly probably have drank from teas that were made from plastic tea bags, or coffee from those plastic coffee cups. We have one set of good data that lets me calculate an exposure to air in a Paris study. So before we get into that, I want to again summarize what we talked about this morning, that most critical foods are not sampled. So I can do a little math calculation about the air, and I know that there's some in clams, but did you know that they feed clam viscera to pigs? And when you look at how much lysine, how much protein a pig needs to grow, and you just did the math, and if 10% of the diet was clam viscera, we could add it up to say, boy, there's a lot of microplastics in that source. I have no idea how much we eat. There's studies seldom provide mass, and when they do, it's not in the media that I could evaluate. And there's seldom small particles. We've heard all this. The health effects are limited to worker studies and implants. People have received implants, and we watch the translocation of particles through the body. Very limited. And in all that data, we have no good dose-response data. I remember seeing Bart this morning had that nice slope. We don't have any good information that gives us a dose-response curve for us to evaluate health, but let's pretend we have some. We do have a little bit of health data, and I can make 2 sets of slides. This one I have a much larger version that has many different plastics in it. This is for the worker-related studies, and we can do one. This one I use to relate inhalation. And we can do the same one for the implant studies, and I'll draw the same conclusion with both of them. But here we have a list of studies, and I've grouped them according to plastics. So here's polyethylene, polypropylene, and nylon. Nylon, when I look at the workers, their health effects are respiratory effects and GI cancers that we see. And we see in the animal studies that were related to these kinds of exposures, we see that there's lung inflammation was more than the natural fibers. And we also see that in the numbers of the populations that textile workers in particular that went from working in cotton and wool and then moved to synthetics. So that's important information. We also know that it was qualitatively dustier environments. So when people worked in dustier environments, they had more health effect. And we know that people that worked many more years had more effect. But then we look at the numbers that were measured in their occupations, and we see very little data. But what we see is this is occupational total dust. So it's not what EPA samples. So they're somewhat small particles, somewhere maybe a middle number of around 10 microns. And they had respirable dust, which they had a 5-micron cut, so 5 micron and below. When we look at this, somewhere around half of the particles in these occupational studies, half of the particles were below 5 microns. And so we can't really relate very well the size of these particles with regards to the health effects, but we know from other inhalation studies that small particles are very important. So what are the implications for sampling? In this study, we can relate to some degree the mass of their particles that were small to a health effect. We have milligrams per meter cubed per year. And so we have somewhat of a relationship to compare something to. So I would hope that if I ever get this data in the environment, I would be able to compare it to this. I want to move on to PVC. PVC, and this is particulate matter. Why I stress that? Because we also look at PVC studies for a dissolved PVC. But for those that were particulates, there's several studies. We see respiratory effects, GI cancers, and we also see, in addition, so separate from these, lung cancer, liver tumors. Pretty important. So there's a unique effect and a reason to separate PVC from the other particles. We also saw that in a mouse study that they recently took the same particles that were found in the workplace and stuck it on lung tissue. And they also dissolved it. So they found that the particles were more toxic than the solution. So this is pretty important. Often we try to make things dissolve to make it more bioavailable when we look at the gut studies. But here we find out that might not be a good idea. We see that people that worked longer had an increased risk, 20% per year. And we see in the mouse studies that the health effects had some markers that were similar to silica after 2 days, but not after 90 days. And we have no very long-term studies to go from. But from that, as long as I'm starting to relate a health study to silica dust, I know silica dust very well, and when I go and sample silica dust, I want the total dust content and then the percent silica. So that when I'm thinking about if I was to have some inhalation data in the air, I would want to have exactly that. I would want to know the total number of particles that are impacting plus the percent of the varying kinds of plastics. Finally, we move to aramid. So we all know this is Kevlar, very popular. Unfortunately, we don't have too many human worker studies, but we have studies of people investigated what worker exposures might have been. One's on human epithelial cells, and we also have an animal study. And what we find is there's protein markers indicate as toxic as 2 of the forms of asbestos. That's pretty important. But we also find that some indication that it might biodegrade in the lungs. So something a little bit different there too. So we have, in this case, just for the few that I showed, different toxicities associated with the different particles. The mass and count were both related. So particle number and mass of particles were related. And they did a very good, so we have a dose-response curve, 0, 1, on the way up to millions of particles, but it's per centimeter squared. And so, because they're doing on tissue, or they do it on cells, and so there's really no good relationship directly back to my inhalation rate. So what's the implication? I would then want to kind of sample it the way I sample asbestos. So here I just made the problem even bigger. You should all be sampling using every different kind of method there is out there. So here's the data I have, and not to criticize, this is the best data that's out there for me to do any math on. So Dris's work in 2 apartments and one workplace, several times during a year, so it was 4 times during a year. Large volumes were collected, so very good data. I see the distribution of particles. Unfortunately, the range goes from 50 microns to 4,800 microns, very large. His lens was only 16 times, so he has only the ability, they had only the ability to see 50 microns and larger. They did do FTIR confirmation of 28 of the fibers, but there was thousands of fibers, and you're picking them. So I've tried picking them myself, and I tried picking cellophane so many times, and it kept going back down to the filter. So So for Bart to be somewhat happy, we did have a blank sample. We don't have a positive control, but we did have that. And we have some sort of a bias. But the good information is 33% of those 28 fibers had petrochemicals, so there's microplastics out there. Oh, I forgot to indicate. The AP is anthropogenic particles. So let's call them microplastics for now. COSA, also, I can follow the same line of logic. Although he did not have FDR conformation, he did have a little bit better zoom lens, so he can get down to 10 microns. If you remember from the last slide, I wonder if I can go back. But last slide, how small these particles are. I forgot to point to this. These were 6 microns by 0.4 microns. That's the median length. So these are all very small. This was respirable dust. They did not say a cut, but usually when you use that method, it's around, well, for other kinds of dust. So I don't know plastics too well, but other kinds of dust, it would be around 4.5 microns by the method they use. So somewhere around 5 microns is the thing that I want. And what am I getting? I'm getting tens and 50s of microns. So you can see the majority of the particles that they looked at. And if you remember again from the Bart's distribution curve, as we get finer and finer, we're expecting to see some more. We don't have that information. But let's use this anyway. And I can use it and a little bit of math. This is not a sphere, but that's a sphere. And I can use a little bit of math. And what other people have told me was the distribution of the types of plastics that are out there, and I can use their densities to give me a mass. So if you remember, we had 3 models that I want to look at. One's the mass model, one's a particle number model, another one is a total mass at below a certain level that has a % of the plastic I'm interested in. So I can't do all that, so I'm going to use my calculations. This is one of the tests that I'm choosing is the 49. It had a little bit smaller particles, had more in the 50 range. So I wanted to see how many of the smallest particles I could find were. And I went and did the math. I broke it into 4 compartments, so because they only counted things in certain categories and kind of applied the math. So when I do that, here's the big uncertainty. Here's the big range if I applied the different mass for the different size particles. So a big range. But let's use the average of that. I can calculate my particles per day that I get inhaling. I could do it, divide it. I can find out, because I breathe 16 cubic meters, what my total mass a day would be. I can divide it by my body weight or my lung tissue size. And so I have many ways that I could compare this other data to, but for the proper diameter of the particles. So we do the same for water. And so we have a mass for the particle. So at ATSDR, we don't have a tox profile for microplastics, so I'm at a loss. So I'm going to pretend. So if all microparticles were antimony, we have a tox profile for antimony, I'm going to follow the process. So we already calculated an air concentration. I could also use a dose or so forth, but within our tox profile, we have what's called a minimal risk level, and it's a guidance. It's a non-cancer effect level. So we look at health studies, and we derive them for acute exposure, so 1 day to 14 days, intermediate 14 days to a year, and then chronic for longer term. So I can look it up in the antimony tox profile, and it's a way for me to work down the process. It actually is a way of me eliminating things that aren't toxic. So I look at it, and I look at the acute MRL, and I say, oof, it's not an acute problem. Then I look at the MRL for chronic exposure, and it's higher. So in my process, I would then go and review the literature. I do the same for water, and I find that it's higher than the intermediate MRL, oral MRL. So then I would go and look at the literature. 2 points, actually, I could go down, there's pages and pages of the individual studies, but I find that it was in the inhalation study, it was good enough information for a female rat. Actually, that's where it was both sexes of rats, but it was found in female rats, to calculate a benchmark concentration. And then I look deeper in. There's low effects that had no effect, and there's low exposures that had no effect. There's low exposures that had some effect, and there was a slope. So I had pretty good data to assess it. So if I feel confident in the data, I also look over to see the uncertainty factor of 30, because we're relating it from an animal, and we also examine it, and it's not so serious in effect. So I feel more and more confident about using my MRL to say whether or not I'm protected, and I wind up going down chasing this pathway a little bit further. Unfortunately, I find for the water, they have a NOEL and they have low Ls, but I find in order to, what they thought increased the toxicity, they dissolved the antimony. And so when I look down into the studies, it doesn't relate to my particle at all. So, but there's other ways of dealing with that in other mathematics. But so we'll stick with the air for now. So when I look at the air, I have other occupational exposures. 91 workers versus 42 control workers at glass manufacturing and plastic product engineering facilities. Again, not all plastics are antimony. In fact, very few are. But here we have concentrations. And so here we have a fairly not so serious effect level of immunity demonstrated, and we have several different concentration groups that were available. We do not have this data for all the microplastics industries that are out there. We do not have this granular of data where we can break down concentration distribution so we have a linear slope. That would be wonderful to obtain, and we can go back to the studies. People are getting exposed to it right now. So it's available out there, but the data's not. So again, this is kind of like the summary slide. Changed some of the words, but I just want to point to the red lines, and that is we need to measure whatever you want to call them, nano and micro, depends on the chemical, but bioactive size microparticles, so whatever that means. But we think 100 in some cases, but we think, often 20, and then clearly, since we're so used to looking at particles that are 5 and 2.5 microns, at least for inhalation, that's pretty important numbers that we should be gathering. We need animal effect studies that represent the people, and we need to collect it in a way that's comparable to our exposures. So those of you that are designing the studies in the lab, we hope that you actually do the particle studies. So that's all the uncertainty. Sorry. Here's what we're doing about it. We finally created a strategic plan last year to focus on some things because many of us had various interests, and many of us kept going into the nanomaterials world because we thought that was the best place to mine the data from. We have a much more focused effort. We established a repository on max.gov that we first were sharing with all our HHS partners, but it seems that we have a great number of folks from various places accessing it. We hired an ORISE fellow. He's here, right here with us. And we prioritize a systematic review. Actually, he's doing a more focused review. Currently, we developed some manuscripts and abstracts. We drafted some drinking water and surface water sampling methods, and that's for the other reason that to try to normalize and standardize what people are doing out there. So I visited 3 of the universities, and I said, at least if some of your samples, if I can take some representative number of samples, and I can apply my methods just so I can divvy it up by particle sizes. And then actually, Anil is here. I shared with him 6 slides from the Hudson River from this year that was taken from wastewater treatment plants. So hopefully we can all, if we start sharing the data and looking at the things through a different set of eyes, maybe we can find a method that we can establish a comparable data with. So this is an old slide. It was over a year ago. I think there's hundreds of publications that were there that were broken into different media. It started out being media, then biota. So things that have various implications. Of course, overwhelmingly, the slide that's for ecological studies has thousands of files in it. So this is kind of what we're doing. This is me. I want to just give a call out to the original, used to be a nanomaterials and microplastics work group of Steve Pappas, Candace Hunter is here, Custodio Mwanga, Janet Telfer, and Julia Carroll. With that, I'm available for questions.